Welcome to Brain Vision.
In this problem on the topic of magnetic forces and the magnetic field, we are told that a shunt-wound DC motor with field coils and rotor connected in parallel operates from a given power line. We are also given the resistance of the field windings as well as the resistance of the rotor, and we are told that when the motor is running, the rotor develops an EMF. We want to calculate the field current, the rotor current, the EMF epsilon, the rate of development of thermal energy in the windings, the rate of development of thermal energy in the rotor, the power input to the motor, as well as its efficiency. So in this problem, we know that the field and the rotor coils are in parallel. So the voltage across them, VAB, is equal to the field current, IF, times the field coil resistance, RF, and across the rotor, this is epsilon plus the current across the rotor, IR, times the resistance of the rotor, RR. And we also know that the total current I is equal to the field current plus the rotor current, IF plus IR. Now, capital I is the current drawn from the line. The power input to the motor, P, is equal to VAB times the current drawn I. And we also know that the power output of the motor is the power input minus whatever power losses occur due to the resistances and the friction. So let's find first the field current, IF. So we know IF is equal to VAB over RF. So that's 120 volts divided by the field resistance, the field coil resistance of 218 ohms. This gives us the field current to be 0.55 amperes. In part B, we want to calculate the rotor current. So the rotor current, IR, is equal to the total current minus the field current. So it's I total minus IF, which is the current drawn from the line 4.82 amperes minus IF 0.55 amperes, which gives us the rotor current to be 4.27 amperes. And that's the current across the rotor coils. Now, for part C, we want to calculate the EMF epsilon. We know that V is equal to epsilon plus IR RR. And so from here, obviously, we can rearrange and we can solve for epsilon. So epsilon is VAB minus IR RR. And all of these values are known, so we can calculate this EMF. So the rotor EMF is VAB 120 volts minus 4.27 amperes for IR times the resistance across the rotor of 5.9 ohms. And so this gives us the EMF developed by the rotor to be 94.8 volts. So that's our answer for part C. Now, for part D, we are asked to calculate the rate of development of thermal energy in the field windings. So the rate of development of thermal energy is the power across the field windings. So we'll call it PF, and we know the power is simply I squared times R, so I squared F times RF. and this is 0.55 amperes squared times 218 ohms, which gives us the rate of development of thermal energy to be 65.9 watts. And that's our answer for part D. Now for part E, we want to calculate the rate of development of thermal energy, or the power, across the rotor. So this we'll call it PR, and PR is equal to, again, I squared R. So it's I squared R times RR. So we substitute our values in this, and we get 4.27 amperes squared times 5.9 ohms, which gives us the thermal energy development rate, or the power across the rotor, to be 108 watts. Now for part F, we want to calculate the power input. So the total power input is equal to V times I. So that's VAB, 120 volts, times the total current drawn, 4.82 amperes, which gives us the total power input to be 578 watts. So that's the total power input of this motor. And finally, we want the efficiency of this motor. So the efficiency is equal to the power output over the power input. So the power output is equal to the total power, 578, minus the power losses across the field coils and across the rotor. So that's minus 65.9 watts minus 108 watts minus 45 watts divided by the total power of 578. And this gives us 359 watts divided by 578 watts, which gives us the efficiency to be 0.621, or 62%.